Hello and welcome. In this video, we're going to wrap up our unit on polynomial functions by talking about key characteristics of the graph, some of which we have already talked about and some of which are new, but we're going to put it all together with polynomials. Then we're going to talk about even versus odd polynomial functions, not talking about the degree, but talking about the behavior and what it means for a polynomial function to be even or odd. And lastly, we're going to wrap up by writing a polynomial function from a graph. So let's go ahead and jump right in. So one of the main things we've talked about with polynomial functions in this chapter are their roots or their zeros. So let's kind of summarize what we already know and then just add one new thing in. So we've talked about zeros, which are the values that make a polynomial function equal to 0, where we cross the x-axis. Those are our zeros. We talked about the same thing when we learned about quadratics. We've talked about factors, where x minus k is a factor of the polynomial. We've talked about solutions, where k is that solution or the root that makes it equal to 0. So all of these kind of tie together. And we've talked about x-intercepts, which is what we think about when we're looking at the graph, which is the place where we cross the graph, k, 0. So all of these words tie together, but that vocabulary needs to be understood, the differences between them. The 0 versus the factor versus a solution versus an x-intercept. But the key idea is we're talking about the x values where we are crossing the x-axis for a polynomial function. In previous chapters, we've talked about where a polynomial function is increasing, meaning going up, and where it's decreasing, meaning going down. So we've also talked about increasing versus decreasing. The last new thing that we're going to add here are what is it called when we switch from increasing to decreasing? And those are called local or relative extrema. So that's where we change from increasing to decreasing or from decreasing to increasing. So these points here are relative or local extrema, and they have specific names. When it's the highest point, it's called a local maximum. So the y coordinate, this is really important, of a turning point where we're turning around is called a local maximum of the function when it's higher than all of the points in the general neighborhood. So everything right to the left and right to the right of it. A y-coordinate of a turning point is called a local minimum when all the points are higher than it, when it's lower than all of the points nearby. So basically, anytime you see sort of like a parabola vertex, that's going to be a relative or local extrema. And when we're identifying those, we're going to talk about the maximum value being the y and the location that that's happening at being the x. So let's look at some graphs and identify these characteristics from a graph. All right, so here we have a couple of graphed polynomial functions, and we're going to use those graphs to identify the key characteristics and information that we can see. So let's start with increasing. Increasing means as I'm tracing from left to right, I'm going uphill. So here, I'm going up until I get to that point and then I stop. And then here, I'm also going up from left to right. Similarly, over here, in this green region here, I am increasing. And we're going to write those increasing intervals so that we can describe the interval over which we're increasing. So on number 1, it's going forever down. So we're starting by increasing, so negative infinity, until I get to the x value of this point, 0.639. Now I'm increasing, I'm describing the behavior. I'm not describing the height, I'm describing how I'm behaving. That means we're talking about the x's. This is going to be connected to or in union with this interval from 4.694 and then forever up, which means to infinity. Why don't you go ahead and pause the video and identify the increasing interval on number 2. Okay, hopefully you had time to do that. So we're looking at the x values here. So there's only one interval. There's only one interval of increasing here, negative 0.786 until 2.12. So we just write it as one interval. Now, if you're feeling ready, go ahead and pause the video and work on decreasing. Otherwise, watch me do number 1 and then you can work on number 2. we're decreasing in between. So we're still talking about the x values when we're talking about increasing and decreasing. So for number 1, I'm decreasing from 0.639 until 4.694. And notice these should all be the same numbers, right? From negative infinity until 0.639, I'm increasing. Then from 0.639 to 4.694, I'm increasing. Then I pick up at that exact value that I left off. So these should be connected. They should have the same numbers. I should be able to trace the behavior from negative infinity to positive infinity. So go ahead and pause the video and write the decreasing interval or intervals on number 2. So hopefully you got that there should be 2 here. I am decreasing from negative infinity forever left until I get to negative 0.786. And then again from 2.12 to infinity. Okay, zeros and roots, those are just the points where the polynomial function is crossing the x-axis. And we're going to go ahead and list those as x values. You could also list them as ordered pairs, but let's identify those where we are crossing the x-axis. That would be at these 3 x values, or at these 3 coordinates. So this is going to be when x is equal to -1 and 3 and 6. So go ahead and pause the video and find the zeros and roots on number 2. All right, hopefully you had time to do that. So we have roots when x is equal to -2, +1, and +3. And also, just keeping in mind, if we have 3 roots, what we learned is that this should be some cubic function, or we know it is at least a cubic function because it could also have imaginary solutions. Okay, the next 2 are review, but I know that they have confused some people in the past. F of x greater than 0 is asking when is your function above the x-axis. So just like with increasing and decreasing, we're going to talk about intervals and we're going to talk about x values. So I want to talk about everywhere that my graph is above the x-axis. So that's happening in those 2 places. So it's happening, again, looking at the x values between -1 and 3, right? It's happening here to here. And then it starts happening again at 6, and it's then forever above the x-axis based on what we can see happening from the graph, which means that it is below the x-axis on the opposite intervals. So it's below the x-axis from negative infinity until we get to -1. And then in between 3 and 6 down here, it's below the x-axis. That looks like a smiley face. So in between 3 and 6. So go ahead and pause the video and identify those intervals where we are above or where we are below the x-axis on number 2. Then unpause the video and see how you did. So we're above the x-axis from negative infinity to -2 and from 1 to 3 on number 2, and below in between, so -2 to +1 and 3 to infinity. Now let's add our last piece where we have relative extrema or local extrema. So I'm going to go ahead and first circle those points. So this point here is a relative extrema or a local extrema, and this point here. So there is a local max. What is this maximum value? It's the y value, 10.373. And when does that happen? It happens when x is 0.639. There's a local minimum of, what is that value? -6.299. When does that happen? It happens when x is 4.694. So we can see 2 similar points here, and there could be more than 2, but in both of these examples, we just have 2. See if you can fill in the blanks for local max and min on number 2. All right, hopefully you've had time to work through those. There is a local maximum. What is the maximum value? Here is the maximum value. So of 4.061, when x equals what at that point? 2.12. There is a local minimum of what? What is that? It's -8.209. When does that happen? When x is -0.786. So really this last portion here, our local extrema, or local maxes and local mins, that is the new part. So we're talking about the highest value and the lowest value in a general neighborhood. Now let's move on to something new. So now we're going to move on to determining if a function is even or odd. And don't let these instructions deceive you. Being even or being odd isn't just talking about the highest exponent. It's not just talking about the degree of a polynomial. Even functions have something special about them. They are symmetric about the y-axis. So every quadratic is not an even function, but those that have symmetry about the y-axis, those particular quadratics are even. So what does this mean? What it means is symmetric about the y-axis. We know that that means there's a transformation, right? Symmetric about the y-axis means that we're looking at f of negative x. And we're saying that that is exactly the same as what we get if we just plug in regular x. What that means is if you think about the quadratic, I'm going to just write a basic one here, y equals x squared. If we plug in -1 and if we plug in +1, we get the same exact output, right? The output is the same because it's symmetric about the y-axis. We could fold it along the y-axis. So how do we determine if a function is even? What we do is we let x equal -x and we simplify to see if this statement is true, if we end up with the exact same function. So let's look at number 3, and let's check to see if number 3 is even. So what we're going to do is we're going to plug in -x. I'm going to replace that in red so you can see it a little better. Everything else is going to stay exactly the same. Well, f of -x, if I simplify inside, I'm squaring -x. Well, that's going to make this -x become +x squared plus 5. What I want you to notice is that this is exactly the same as what we started with. If I plug in 1, I get the same thing as if I plug in -1. It is symmetric about the y-axis. It is even. So since f of -x is equal to f of x, f is even. What that means is it also says then describe the symmetry. This is symmetric about the y-axis. We can fold it over the y-axis and everything lines up perfectly. I want you to pause the video and check numbers 4 and 5 and see if they are even. Then unpause the video and see how you did. All right, if I plug -x in here, I'm going to get to the 4th minus 5 times -x cubed. Sorry, I wanted that -x to be in red. So here we're going to get g of -x is equal to, well, -x to the 4th is just going to be x to the 4th, but this is going to be minus -x to the 3rd is going to be still -x to the 3rd. So this is going to be g of -x equals x to the 4th plus 5x to the 3rd. The sign is going to change. So the key thing here is this sign changed. So it's not exactly the same as the original function. This is not exactly the same as this. So number 4 is not even. If you didn't already pause the video and try number 5 on your own, do it now. All right, h of -x is going to equal 2 times -x to the 5th. What happens when I put -x to the power of 5? The negative is going to stay because it's an odd exponent. So this is going to be h of -x is equal to -2x to the 5th. And I'm asking myself, is this identical to this? And no, it's not. So the only problem that's even is the first one. Because when we plug -x in, we get the exact same function that we started with. So what does it mean to be odd? An odd function, when you plug in -x, you get a reflection of the entire function. So the key thing for odd is that instead of for even, nothing changes. Nothing changes. For odd, everything changes. Everything changes sign. Odd functions have special characteristics as well. Odd functions are symmetric about the origin. If you folded your graph along the origin or overlapped across the origin, everything would line up. So if you have a point x, y, you also have a point negative x, negative y. Everything changes sign. Changing the sign of the x changes exactly the sign of the output. So how do you test if a function is odd? You do the exact same thing. You let x equal negative x, and you're looking to see, is my function exactly the opposite? If I plug in negative x, do I get the opposite of everything? So we already did the legwork for this on numbers 4 and 5. On number 4, we plugged in negative x, and we got positive x to the 4th, and we got plus 5x to the 3rd. So what I want you to notice is that the 5 changed sign, but the x to the 4th did not change sign. So this is not even because something changed. It's not odd because everything didn't change. So this is neither. It would be odd if everything changed sign, but not if just some things change sign. So if nothing changes sign, it's even. If everything changes sign, it's odd. If some stuff changes, it's just neither. So on number 5, we started with 2x to the 5th, and we plugged in negative x, and we got negative 2x to the 5th. What that means is when we plugged in negative x, we got exactly the opposite of the function, which means that number 5 is odd, which means it is symmetric about the origin. So the key idea for even and odd functions, just plug in negative x. See what happens. If everything changes, it's odd. If nothing changes, it's even. If some stuff changes, it's neither. All right, we're going to look at one last topic, and then we're going to wrap up this video. All right, the last thing we're going to talk about is modeling with polynomial functions. So what we're going to do is we're going to write a function given the graph. So key things I want to point out. I'm going to tell you what the degree of the function is. So both of the functions we're going to be writing today are going to be cubic functions, which helps that we can see the 3 zeros on the graph. That's going to help us write our functions out. We're going to use intercept form for cubic, which looks a whole lot like intercept form for quadratic, except there's 3 of them because it's to the 3rd power. So here's how we're going to go about doing this. The very first thing we're going to do is we're going to identify the zeros or the roots, and we're going to write them as factors. So if we look at number 6, I see a root at negative 4, so that's x plus 4. I see a root at positive 1, so that's x minus 1. I see a root at 3, so that's x minus 3. So step 1, write the zeros as factors. Also, there's an a value here that I need to find. I needed to see if there are any stretches or shrinks. So I'm going to put an a in front. Then, just like we did with quadratics, we're going to plug in any other point to solve for a. So here, the only other point that's on my graph is 0, negative 6. So I'm going to say with the point 0, negative 6, I can find a. So a is going to be 0 plus 4, 0 minus 1, 0 minus 3. So I'm plugging 0 in for all of those x values. And then I'm going to go ahead and simplify. A times, this is going to just be 4 times negative 1 times negative 3. So 4 times negative 1 times negative 3. That's going to be positive 12. So a times 12 is negative 6. So I'm going to divide both sides by 12. So a is going to be negative 6 over 12, or negative 1/2. And then step 3, rewrite it as a function. F of x is going to equal negative 1/2, that's what we found a to be, times x plus 4, times x minus 1, times x minus 3. Now, unless the directions specify otherwise, I'm okay with you leaving this in factored form. I don't need you to multiply this out and write it as a polynomial. If the directions specifically tell you to write it out, then you're going to need to multiply out the same way we have been doing. But I'm going to just for right now say you're probably just going to be able to leave it in factored form to save time. So I'm going to encourage you to pause the video and work through number 7 on your own, and then unpause the video and see how you did. All right, so the first thing I'm going to do is identify all my zeros. I see one at -3, so x plus 3. I see one at +1, so x minus 1. And I see one at +2, so x minus 2. Oops, sorry, that cut off a little bit. Then I need to find a. So the only other point I see is 0, 3. So with the point 0, 3, 3 is going to equal a. Now, if I plug in 0, this is just going to be 3. If I plug in 0, this is just going to be -1. If I plug in 0, this is just going to be -2. So 3 equals 3 times -1 times -2. Well, that's going to be 3 equals -6a. If I divide both sides, not -6, +6a. Negative times a negative is a positive. Then I'm going to divide both sides by 6. That's going to give me that a is 1/2. So f of x is going to equal +1/2 times x plus 3 times x minus 1 times x minus 2. So key things in this section. First of all, we added a new vocabulary to our new vocabulary terms to our repertoire, and that are local maxes and local mins. And that is sort of like a little parabola vertex somewhere within the function, a point that is the highest or lowest point within a particular portion of the graph. The y-coordinate is the local maximum or local minimum. Where that happens, the x value just tells you when you have a local max or min. But we are talking about the local maximum value, the local minimum value. So we're talking about y. We also reviewed increasing, decreasing, zeros or roots, where the function is above and below the axis. Next, we talked about even and odd functions. An even function is a function that is symmetric about the y-axis. What that means is for every x we plug in, we'll have two y values that are the same, whether I plug in -x or +x. To check if something is an even function, you plug -x in and simplify. If what you get is exactly the same function that you started with, so if f of -x is equal to f of x, then our function is even, which means it's symmetric about the y-axis. A function is odd if when you plug in -x, it changes everything. So f of -x is equal to -f of x. An odd function is symmetric about the origin, and we can check that by simply plugging in -x. If -x changes the sign of every term, our function is odd and therefore symmetric about the origin. If only some terms change, then our function is neither even nor odd. Lastly, we talked about writing a polynomial function given a graph, and we looked specifically at cubics, and we wrote them in intercept form. So we found the zeros and wrote those as factors. We plugged in another point to find a, and then we rewrote our function in factored form. And that's really all that we covered in this video. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.